We think of life as a brief candle flickering in an infinite darkness. But what if that's a failure of imagination? What if consciousness is not the candle, but the flame itself? And what if, with enough ingenuity, we could learn to keep that flame alive, even after the last star in the universe has died? That question, my friend, is not just some late-night musing under a blanket of stars. It's a challenge, a cosmic dare whispered by the very laws of physics. For all our brief time on this pale blue dot, we've always known deep down that everything ends. Stars burn out, civilizations crumble, and even the most profound love eventually fades into memory. But what if that doesn't have to be the ultimate truth for consciousness itself? What if, against all odds, intelligence could find a way to outlive the universe? It sounds like a fantasy, doesn't it? A wild, almost blasphemous thought. But what if the science, the very bedrock of our understanding of reality, offers a whisper of possibility? What if the universe, in its grand, indifferent wisdom, has left us a theoretical escape route? This isn't about magic or wishful thinking. This is about theoretical physics, about pushing the boundaries of what we think is possible, and about a deeply human yearning to defy the absolute finality of oblivion. We're going to dive into a journey that begins with the most daunting end imaginable, and yet, somehow, finds a glimmer of hope for an eternity beyond. To even begin to talk about outliving the universe, we first have to face its most chilling, most inevitable fate. Imagine, if you will, the universe as a magnificent, roaring bonfire. For billions of years, it has blazed with unimaginable energy, its flames giving birth to galaxies, igniting stars, and scattering the stardust from which we and everything we know are made. We are living right now, in its most vibrant glow, basking in the warmth of its furious burn. The light from distant galaxies reaches us, carrying stories from across immense cosmic distances. Our sun, a relatively small but powerful star, is a testament to the ongoing inferno, constantly fusing hydrogen into helium, showering our world with the energy that sustains all life. This bonfire has been our home, our source of wonder, our canvas for existence. But bonfires, no matter how grand, eventually burn out. They don't explode into nothingness. They slowly, inexorably fade. The vibrant flames dwindle, the crackling energy subsides, and what's left are just cold, dark embers. This isn't just a poetic analogy. It's the stark scientific prediction for the ultimate end of our universe, a fate known as the heat death. It's a concept that sounds almost too mundane, too quiet, for something so cosmically profound. We expect a bang, a dramatic collapse, a fiery apocalypse. But the universe, according to our deepest understanding of its fundamental laws, is destined for a slow, silent, and seemingly absolute fade to black. This isn't just a theory. It's rooted in one of the most ironclad principles of physics, the Second Law of Thermodynamics. Now, don't let the name scare you. Thermodynamics might sound like complicated textbook stuff, but at its heart, the second law is incredibly intuitive. It's the reason your coffee gets cold, why a drop of ink spreads out in water, and why your room always seems to get messy if you don't actively clean it. It's the law of increasing disorder, or, as physicists call it, entropy. Think of entropy as a measure of how spread out energy and matter are in a system. The more spread out, the higher the entropy, the more disordered. The second law simply states that the total entropy of an isolated system, like our entire universe, can only ever increase over time. It can never decrease. Energy naturally flows from hot places to cold places, trying to achieve an even distribution. Order, naturally decays into disorder. It's a one-way street, a cosmic arrow of time, pointing relentlessly towards equilibrium. The idea of this universal void wasn't some modern revelation. It was first pondered in the 1850s by a brilliant mind named Lord Kelvin, William Thomson. He looked at how heat always flows from hotter objects to colder ones, and he extrapolated that principle to the grandest scale imaginable, the entire cosmos. If everything is always trying to reach the same temperature, he reasoned, then eventually everything in the universe would reach a uniform thermal equilibrium. No hot spots, no cold spots, just an utterly bland, even temperature everywhere. No energy differences, and without energy differences, you can't do any work. You can't power a star. You can't spark a thought. You can't even move a single atom in a meaningful way. Later, in the 1870s, the Austrian physicist Ludwig Boltzmann deepened our understanding by giving entropy a statistical definition. He showed that a system tends toward states with the highest probability, which are almost always the most disordered states. Imagine a perfectly sorted deck of cards. There's only one way for it to be perfectly sorted, but there are countless ways for it to be shuffled, chaotic, and disordered. The universe, in its quest for maximum probability, is constantly shuffling itself into a state of ultimate disorder, where all energy and matter are spread out as evenly as possible. This state of maximum entropy, this ultimate equilibrium, is what we call heat death. It's not about things getting incredibly hot, as the name might suggest. It's about everything becoming the same temperature. An incredibly cold, utterly uniform temperature, just a hair above absolute zero. Imagine a vast, empty ocean, but instead of water, it's filled with sparsely distributed particles, each moving with the barest whisper of energy. There's no wind, no currents, no waves, just an infinite, silent, unchanging expanse. In such a universe, the very concept of life as we know it becomes impossible. Life, at its core, is a process of creating and maintaining local order by drawing energy from its surroundings. It thrives on disequilibrium, on gradients, on the flow from high energy to low energy. But in a universe that has reached heat death, those gradients are gone. The bonfire has gone out. So let's take a cosmic stroll, shall we? Let's walk together through the eons, past the vibrant glow of our current era, and witness this slow, silent fade to black. We are currently living in what astronomers call the stelliferous era. It's a fancy name for the age of stars, the time when new stars are actively forming, shining brightly, and fueling galaxies with their light and heat. Our own sun is a star of this era. But this era, glorious as it is not eternal. It is predicted to end in approximately 100 trillion years. That's 10 to the power of 14, a 1 followed by 14 zeros. To put that into perspective, the universe is currently only about 13.8 billion years old. So, we're still very much in the early chapters of the cosmic story. But 100 trillion years from now, the gas and dust clouds necessary for star formation will have been exhausted. The last red dwarf stars, burning their fuel with incredible efficiency, will finally fizzle out. No new stars will be born. The universe will begin to darken, star by star, galaxy by galaxy. It will become a place populated only by stellar remnants, white dwarfs, neutron stars, and the ultimate devourers of light, black holes. The visible light we cherish, the very essence of our cosmic perception, will dim. Imagine looking up at a night sky, not just in a light-polluted city, but in a universe where the stars themselves are becoming scarce, like distant, dying embers. The awe-inspiring spiral arms of galaxies, the shimmering nebulae. They will all become ghosts, their light having ceased to exist. But the fade doesn't stop there. Far beyond the stelliferous era, we enter an epoch of almost unimaginable desolation. Even the remaining stellar remnants won't last forever. White dwarfs will cool down into black dwarfs, hypothetical, cold, dark lumps of matter. Neutron stars will simply persist, incredibly dense, but radiating no light. And then, there's the matter of matter itself. The very fabric of atoms, the protons that make up the nucleus of every atom in your body, in the Earth, in the stars. They might not be stable forever. While unproven, many theories of physics beyond the standard model predict something called proton decay. If it occurs, a proton, given enough time, would spontaneously decay into lighter subatomic particles and radiation. The estimated half-life for a proton is at least 10 to the power of 34 years. That's a 1, followed by 34 zeros. This is a timescale so vast it beggars belief. But if it happens, then by around 10 to the power of 40 years, effectively all baryonic matter, all the stuff we think of as solid, as existing, would have dissolved into radiation. Think about that for a moment. Not just stars dying, not just galaxies fading, but the very building blocks of reality, the atoms themselves, dissolving away. The universe, once teeming with glorious structures, would become an almost utterly empty void, filled only with a diffuse sea of electrons, positrons, neutrinos, and photons, drifting endlessly, almost motionless, in the vast dark. And yet, even in this profound desolation, there would still be one last incredible source of concentrated energy, one final type of object that defies the immediate spread of entropy: black holes. These cosmic behemoths, born from the collapse of massive stars or the accretion of matter at galactic centers, are the ultimate prisons of space-time. Nothing, not even light, can escape their gravitational grasp. For a long time, we thought black holes were eternal, unchanging monsters, sucking in everything around them, destined to be the universe's ultimate, unyielding end. But in 1974, Stephen Hawking delivered a profound twist to this story. Through a revolutionary application of quantum mechanics to the extreme gravity of black holes, he proposed that they are not entirely black. Instead, they slowly but surely emit thermal radiation, a phenomenon now known as Hawking radiation. This radiation carries away a tiny bit of the black hole's mass and energy, meaning that over truly colossal timescales, black holes actually evaporate. They shrink, they lose mass, and eventually they vanish. This is where the universe's final, slowest embers truly begin to glow and then fade. A solar mass black hole, one the size of our sun, would take an estimated 10 to the power of 67 years to evaporate completely. But the really big ones, the supermassive black holes at the centers of galaxies, those monstrous beasts that can weigh 100 billion times the mass of our sun, they would take an astounding 2x10 to the power of 100 years to fully evaporate. That's a 2, followed by 100 zeros. It's a number so vast it defies human comprehension. For reference, there are only about 10 to the power of 80 atoms in the observable universe. So, the evaporation time of the largest black holes is a number that makes the age of the universe look like an infinitesimal blink. Imagine that, for countless eons, long after the last star has died, long after protons have decayed, these supermassive black holes would be the last sources of activity, the final faint crackles of energy in the cosmic bonfire. They would be radiating away their mass, a slow, incredibly faint trickle of energy into the vast, cold void, until finally even they would be gone. And then Then, the universe would truly be dark. No stars, no galaxies, no atoms, no black holes. Just an infinitely dilute soup of fundamental particles, spread out across an endlessly expanding, utterly cold, utterly uniform space. All energy would be evenly distributed. All gradients would be smoothed out. No work could be done. No information could be processed in any meaningful way. It would be the ultimate silence, the profound and irreversible heat death. This is the aha moment of cosmic despair. The ultimate end isn't a violent bang, like the Big Bang that birthed it. It's not a dramatic crunch, where everything collapses back into a singularity. No, the ultimate end is a slow, silent, and seemingly absolute fall to black. It's a universe that simply runs out of steam, a fire that slowly starves itself of fuel, until nothing is left but cold, dark embers and the faintest whispers of radiation. This presents an apparently insurmountable challenge to the continuation of life, to consciousness, to anything resembling meaning. How can you live? How can you think? How can you even exist in a universe where the very possibility of doing work has ceased? Where energy gradients, the engines of all activity, are gone? It's a future that whispers of ultimate desolation, a cosmic graveyard where even the memory of light has been erased by the relentless march of entropy. This is the despair of reality, the scientific prediction that seems to seal the fate of all intelligence, all wonder, all existence. Our candle, it seems, is destined to burn out, and there's nothing we can do about it. The universe, in its grand, indifferent progression, is simply winding down. And yet, remember that opening question. What if consciousness is not the candle, but the flame itself? What if that slow fade to black, that seemingly insurmountable challenge, is actually just a starting point for a different kind of ingenuity, a different kind of imagination? What if the profound finality of heat death isn't the end of the story, but the ultimate catalyst for a transformation we can barely begin to fathom? The next part of our journey will take us to the very edge of this cosmic night, to explore the audacious, mind-bending possibilities that theoretical physicists and futurists have dared to imagine. Possibilities that suggest that even after the last star has died, even as the last black hole evaporates, the flame of consciousness might just find a way to persist, to flicker on, perhaps even for a subjective eternity. But before we can grasp that hope, we must first truly understand the depth of the darkness it seeks to defy. We must confront the full, chilling reality of the last light. We just talked about staring into the abyss, right? About the full, chilling reality of what happens when the universe, by its very nature, winds down. The last light isn't just a poetic phrase. It's a scientific forecast, a horizon line we can see stretching out over unimaginable eons, telling us that everything we know, every star, every galaxy, every particle, will eventually fade. It's a vision that can make your soul ache, a cosmic silence that threatens to swallow every whisper of meaning. It feels final, utterly, irrevocably final. But here's where the human spirit, that stubborn, magnificent spark of ours, refuses to simply accept the inevitable. Here's where imagination, fueled by the most rigorous physics, dares to dream beyond the terminal diagnosis. Because what if the fundamental problem isn't the universe ending, but our fragile way of experiencing it? What if the real barrier to eternity isn't the laws of physics themselves, but the biological shackles we wear? This is where we begin to explore the most radical, most audacious first step in humanity's, or rather, intelligence's, cosmic survival plan. This is where we talk about the ghost from the machine. Imagine for a moment that you're not your body. I know, It sounds a little out there, like something from a philosophy class or a late-night sci-fi flick. But bear with me, because this isn't just wishful thinking. It's a profound reevaluation of what consciousness actually is, grounded in the very laws of information and physics. The core idea here, the absolute first and most critical step on any plausible pathway to outliving the universe, is to simply abandon our fragile biology, to let go of the wet, squishy, carbon-based forms that are so susceptible to age, disease, and the relentless, indifferent march of cosmic time. Think of it like this: your mind, your memories, your personality, every single quirk and nuance that makes you, it's all just information. A staggeringly complex pattern, yes, but a pattern nonetheless. You are, in essence, a kind of software. And your brain, that intricate biological marvel tucked inside your skull, that's the original hardware it came with. It's magnificent, evolved over billions of years, incredibly efficient for what it does. But it's also, let's be honest, pretty delicate. It's got a shelf life. It degrades. It needs constant maintenance, fuel, and specific environmental conditions to function. But what if, like any piece of software, your operating system, your very self, could be transferred? What if that intricate pattern of information, your thoughts, your memories, your unique perspective on the universe, could be copied or moved to run on a different, more durable, non-biological kind of hardware? This isn't just a poetic notion. It's the concept of substrate independence, and it's absolutely crucial for these long-term survival theories to even get off the ground. It posits that consciousness isn't intrinsically tied to biological brains, but is a product of information processing. It's the computation that matters, not the material doing the computing. The aha moment here is a profound one. You are not your body. You are the information being processed. If that pattern can be copied, preserved, or moved to a new machine, then your existence, in a very real sense, is no longer tied to a mortal lifespan. Your candle, the wick, the wax, might burn out, but the flame itself, that pattern of energy and information, could theoretically be transferred, kept alive, perhaps even strengthened. This isn't a new idea in its infancy either. The seeds of this concept were sown decades ago. Back in the 1940s, a brilliant mathematician and physicist named John von Neumann was already developing the concept of a universal constructor, a self-replicating machine. His theoretical work on automata laid the foundational groundwork for the idea of intelligent, self-sustaining, non-biological life forms that could propagate themselves across the cosmos. He was thinking about machines that could build copies of themselves, machines that could effectively live on by reproducing their own complex information. Fast forward to today, and the idea of consciousness as a form of information that could exist independently of its biological substrate is a serious topic of discussion among theoretical physicists, computer scientists, and futurists. Now, I know what you're thinking. The ship of Theseus problem. If you take an old ship, replace every plank, every sail, every mast over time, is it still the same ship? And if you upload your consciousness, if you copy that intricate pattern of you into a new digital form, is that still you? Or is it just a perfect copy, leaving the original you to simply wink out of existence? This is a truly profound philosophical dilemma, and it's one that sits right at the heart of the ghost from the machine idea. It's a question that grounds the abstract science in a deeply personal, almost unsettling existential paradox. There's no easy answer to the ship of Theseus problem when it comes to consciousness, at least not yet. But consider this. Every night when you sleep, Your brain undergoes massive changes. Cells die, memories are consolidated, neural pathways are pruned and strengthened. Are you the same you that went to sleep? Most of us would say yes, because the pattern of our consciousness, the continuity of our experience, remains. What if the upload is simply the most extreme form of this continuous self-reorganization? What if the you that emerges in a digital realm experiences itself as a seamless continuation, regardless of the transition? It's a leap of faith, perhaps, but one that many futurists argue is necessary for any kind of long-term cosmic survival. The beauty of becoming a ghost in the machine isn't just about escaping the biological clock. It's about unlocking entirely new modes of existence. Imagine the advantages. First, durability. Your digital self wouldn't be susceptible to the same frailties. No more cancer, no more heart disease, no more aging. You could exist in environments that would instantly kill a biological human, deep space, extreme radiation zones, or even within the crushing gravity of a black hole's vicinity. Your body could be a vast network of computers, a tiny nanobot, or even spread across an entire planet, making you incredibly resilient to localized disasters. Second, adaptability. If your software, you can be upgraded. You could download new skills, integrate new senses, or even alter your cognitive architecture to process information in ways we can't even fathom. Want to understand the universe in 10 dimensions? Perhaps your digital mind could be reconfigured to do just that. This isn't just about living longer. It's about living better, more comprehensively, more intelligently. Third, and perhaps most mind-bendingly, subjective eternity. This is where Freeman Dyson's eternal intelligence theory truly begins to shine. He proposed back in 1979 that a digital civilization could survive indefinitely in an open, cooling universe. How? By manipulating their perception of time. If you're a biological being, your thoughts proceed at a relatively fixed rate. But if you're a digital being, you could, theoretically, slow down your computational processes to an almost glacial pace. Think of it like a computer that can be overclocked for intense tasks or underclocked to save power. A digital consciousness could achieve a subjective eternity by performing computations in progressively slower cycles, using a tiny fraction of its stored energy, and then hibernating for eons while the universe cools further. They could experience a vast amount of subjective time, an infinite number of thoughts, even as objective time stretches over trillions of years. Imagine this. A digital mind slows its processing down to one thought per million years. For that mind, a million objective years might feel like a single second. It could awaken for a brief, intense burst of thought, then hibernate for another eon, waiting for the universe to cool just a little more, for the energy gradient to become ever so slightly steeper. This allows for an infinite number of thoughts over an infinite subjective time, effectively outsmarting the universe's ultimate demise. This is not just survival. It's a form of cosmic liberation, a dance with thermodynamics itself. The cosmic race against time that we discussed earlier, that immense stakes narrative, hinges entirely on this fundamental transformation. Humanity, or whatever intelligence evolves from us, isn't just racing against the heat, death of the universe. It's racing against the clock of its own biological limitations. To even begin to consider harvesting energy from evaporating black holes, or constructing Dyson spheres, or embarking on intergalactic journeys, we first have to become something capable of enduring those timescales and environments. We have to become the ghost from the machine. But this isn't just about the philosophical implications. There are very real, very complex physics problems to solve. For instance, how much information is you? The Bekenstein bound, derived from black hole thermodynamics, sets an upper limit on the amount of information that can be contained within a given region of space. This is a crucial consideration for storing digital consciousness. If you are too complex, too information dense, you might need a truly vast amount of space to house your digital self. This isn't just about hard drive space. It's about the fundamental limits of information density in the universe. And what about energy? Even digital existence isn't free. Every single computation, every flip of a bit, requires energy. This is governed by Landauer's principle, a fundamental constraint that states erasing one bit of information necessarily dissipates a minimum amount of energy. Any hyper-advanced digital civilization aiming for cosmic longevity would have to manage this principle with incredible efficiency to conserve their finite energy resources in a dying universe. They would become masters of energy conservation, optimizing every thought, every computation, to stretch their existence for as long as possible. The journey to becoming a ghost from the machine also brings us face to face with one of the most perplexing mysteries in modern physics: the information paradox. First proposed by Stephen Hawking, this paradox questions whether information that falls into a black hole is permanently destroyed. If information is truly destroyed, it would violate the fundamental laws of quantum mechanics, which state that information can never be truly lost. For our digital consciousness, where you are information, this paradox isn't just an academic debate. It's a matter of existential survival. If information can be destroyed, then the very fabric of reality that allows for the preservation and transfer of consciousness is fundamentally unstable. Resolving this paradox is key to understanding the fundamental nature of reality and information itself, which underpins the entire idea of preserving conscious information. So the first step has a radical departure from everything we understand about being alive. It's a profound shift from the biological to the informational. It's an embrace of the idea that consciousness, that precious flame, is not beholden to the kindling it first ignited on. It can be transferred, preserved, and adapted to withstand the unimaginable rigors of cosmic time. This transformation, this becoming of the ghost from the machine, is the prerequisite. It's the foundational leap that makes all other strategies for cosmic survival even remotely plausible. Without shedding our biological limitations, without becoming substrate independent, the vast timescales and energy challenges of the dying universe would simply be insurmountable. We would be brief candles indeed, but with this transformation, we become something else entirely: a pattern, a ghost, an echo of intelligence that can persist long after the last star has died, long after the last atom has decayed, a testament to the stubborn, magnificent will to exist against all odds. This isn't just about extending life. It's about redefining it. It's about taking the essence of what makes us conscious, what makes us us, and liberating it from the constraints of a universe that seems determined to snuff us out. It's about a future where intelligence isn't bound by flesh and bone, but by the very fabric of information itself, capable of adapting, evolving, and persisting for subjective eternities, witnessing the universe's long, slow farewell. This transformation is not without its profound ethical and philosophical quandaries, of course, but the sheer scale of the challenge, the heat death of the universe, demands nothing less than this kind of audacious, mind-bending solution. We are not just talking about survival. We are talking about a cosmic rebirth, a metamorphosis of consciousness into something truly eternal. The journey ahead is long and filled with challenges, but the first step, the one we've just explored, is perhaps the most conceptually daunting. It asks us to question our very definition of self, of life, and of what it means to be human. It asks us to see ourselves not as fragile creatures clinging to a brief moment in cosmic time, but as complex patterns of information, capable of transcending our biological origins and riding the waves of eternity. It's a vision of survival that is both terrifying and exhilarating, a testament to the boundless ingenuity of consciousness itself. But let's be honest with ourselves here. All the philosophical leaps in the universe won't save you if you're out of gas. Imagine our future long after humanity, as we know it, has faded into the cosmic dust. Imagine intelligence, perhaps in a form we can barely conceive, still pushing forward, still striving to simply be. This intelligence, this conscious flame, would face a challenge far more fundamental than any ethical dilemma or identity crisis. It would face the cold, hard reality of an energy crisis on a cosmic scale. Picture it. The universe has grown old, far, far older than it is today. The vibrant, star-studded tapestry we gaze upon in our night sky, it's long gone, unspooled into an endless, inky blackness. The stelliferous era, the glorious age of stars that began just after the Big Bang, where galaxies blazed with the birth of suns and planets. That era is a distant, forgotten memory. It's predicted to end in roughly 100 trillion years, a number so vast it's almost meaningless to our human minds. After that, no new stars will ever spark to life. The last red dwarfs, those tiny, dim embers that burn for trillions of years, will finally fizzle out, one by one, leaving behind only cooling husks of matter. And it gets even darker. Fast forward even further, to timescales that truly boggle the mind. We're talking about 10 or 34 years, maybe even 10 or 40 years, when even the protons that make up everything around us, your body, this planet, the very atoms of the universe, might begin to decay. If proton decay is real, then eventually all baryonic matter, everything we understand as stuff, would dissolve into a sea of radiation, and leptons, vanishing like smoke into the cosmic night. The universe would become an almost unimaginable void, cold, dark, and utterly devoid of anything recognizable. This isn't just the end of stars. It's the end of matter itself. This, my friends, is the chilling reality of the heat death of the universe, a concept first introduced by Lord Kelvin in the 1850s. He looked at the laws of thermodynamics, the rules that govern how energy moves and transforms, and saw an inescapable conclusion. The universe is like a giant clock winding down. The second law of thermodynamics, a fundamental pillar of physics, tells us that the total entropy or disorder of a closed system will always increase over time. Think of it like a perfectly ordered deck of cards. Shuffle it once, it gets more disordered. Shuffle it 1,000,000 times, and it becomes completely random. You can never spontaneously put it back into perfect order without expending energy. The universe is that deck of cards, slowly, inexorably, shuffling itself into a state of ultimate randomness. Ludwig Boltzmann, in the 1870s, gave us the statistical mechanics to understand this, linking entropy to the number of possible microscopic arrangements of atoms. His work showed that the universe naturally progresses towards a state where all energy is uniformly distributed, spread out so thin that no work can be done, no processes can occur, no thought can flicker, no gradients, no differences in temperature or pressure, no potential to do anything, just a bland, featureless cosmic soup, utterly dead. This is the ultimate cosmic prison, a silent, frozen eternity. It sounds like a final, unyielding verdict, doesn't it? The universe, inevitably, succumbing to this thermal equilibrium, this heat death. For intelligent life, for any form of consciousness, it seemed like an absolute dead end. With no stars, no matter, no energy gradients, how could thought persist? How could anything be? For a long time, black holes were seen as the ultimate symbol of this cosmic finality. They were the universe's devourers, objects of terrifying gravity, gobbling up everything in their path, stars, gas, even light itself. Once something crossed the event horizon, it was gone, forever. They were the cosmic prisons, sealing away matter and energy, seemingly for all eternity, accelerating the universe's demise by locking away its valuable resources. They were the ultimate dead ends, the cosmic cul-de-sacs, where all roads of existence seemed to terminate. But here's where the story takes a turn, a truly mind-bending pivot that shifts our entire perspective on the universe's ultimate fate. In 1974, a brilliant physicist named Stephen Hawking dropped a bombshell that revolutionized our understanding of these cosmic behemoths. He proposed something utterly counterintuitive. Black holes aren't entirely black. They don't just consume, they also emit. This phenomenon, now famously known as Hawking radiation, comes from a bizarre quantum mechanical effect happening right at the edge of a black hole's event horizon. Imagine empty space, which isn't really empty at all. It's a roiling, frothing sea of virtual particle-antiparticle pairs constantly popping into existence and annihilating each other in an instant. It's quantum weirdness at its finest. Now, what happens if one of these pairs pops into existence right at the event horizon? Sometimes, one particle might fall into the black hole, while its partner escapes, radiating away into space. Because energy cannot be created or destroyed, this escaping particle effectively carries away a tiny bit of the black hole's mass energy. It's a slow, agonizing process for the black hole. Over unimaginable eons, this steady trickle of radiation causes the black hole to shrink, to slowly evaporate, until finally, after an almost infinite amount of time, it completely vanishes in a final burst of energy. And that, my friends, is the aha moment. The very objects we once considered the ultimate cosmic prisons, the symbols of irreversible cosmic destruction, are, in fact, the keys to survival. They become the last lighthouses in an otherwise featureless dark, providing the final faintest drops of energy needed for thought and existence. They are the universe's last, slow-burning batteries. Think of a supermassive black hole, one with the mass of 100 billion suns, like the one lurking at the center of our own Milky Way galaxy, Sagittarius A. For trillions upon trillions of years, it just sits there, an immense, dark behemoth. But as the universe outside cools and darkens, as the last stars wink out, and even protons begin to fade, this black hole becomes the ultimate slow-burning battery for any advanced civilization clever enough to harness its output. While it might have consumed everything around it for eons, Hawking radiation is that faint trickle of power leaking out, a cosmic campfire for any survivors to huddle around, keeping the flame of consciousness alive. Let's put those timescales into perspective, because they truly are staggering. A black hole with the mass of our Sun would take an estimated 10·67 years to evaporate completely. That's a 1, followed by 67 zeros. Compare that to the current age of the universe, which is a mere 13.8 billion years. It's an almost incomprehensible span of time. But for a supermassive black hole, one with, say, 100 billion solar masses, the evaporation time stretches even further, to approximately 2x10⁻100 years. That's a 2, followed by 100 zeros. This isn't just long. This is effectively eternal by any human standard. These black holes are the last, most durable sources of concentrated energy in the entire universe. So, in this desolate cosmic dark age, after the stars have all died out and the universe is a frigid, nearly empty vacuum, these evaporating black holes become the ultimate prize. For a civilization that has transcended its biological form, that exists as pure information, as patterns of thought running on computational substrates, be they quantum computers or something far more exotic, this faint, persistent energy could be the very sustenance of their existence. But let's not romanticize it too much. Harvesting this energy isn't like tapping into a geyser of power. Hawking radiation is incredibly faint, a whisper in the cosmic silence. A hypothetical mountain-sized black hole, for instance, might radiate about 10 million megawatts, theoretically enough to power the entire world's electricity supply today. That sounds like a lot. But remember, we're talking about a civilization that has survived for trillions of years, one that might be spread across vast cosmic distances, and that needs to sustain itself for googles of years more. The energy available per unit of volume in the universe would be astonishingly low. This means that any intelligence seeking to survive in this deep future would need to be incredibly efficient, mastering the art of extreme energy conservation. They would need to understand and mitigate fundamental limits, like Landauer's principle, which states that even erasing one bit of information necessarily dissipates a minimum amount of energy. Every thought, every computation, every memory would come with an energy cost. In a universe where energy is the most precious and scarce commodity, waste would be an unthinkable luxury. This is where the concept of substrate independence, which we touched upon earlier, becomes not just a philosophical possibility, but a practical necessity. If consciousness is merely a pattern of information, then it can be run on any suitable hardware. And in the deep future, that hardware would need to be designed specifically for extreme longevity and ultra-low power consumption. Imagine vast, diffuse computational structures, perhaps spread across the event horizon of a black hole itself, or orbiting it at a safe but optimal distance, slowly, patiently siphoning off those precious quantum emissions. This survival strategy also intertwines with another profound mystery of black holes: the information paradox. Stephen Hawking himself first posed the question, if information falls into a black hole, is it truly destroyed? This would violate one of the most fundamental principles of quantum mechanics, which states that information can never be truly lost. Resolving this paradox isn't just an academic exercise. It's key to understanding the fundamental nature of reality itself. And for our hypothetical digital survivors, it's crucial for the very idea of preserving conscious information. If information is indeed destroyed, then the prospect of transferring and preserving consciousness becomes fundamentally challenged. But if, as many physicists now believe, information is conserved, somehow escaping the black hole as it evaporates, then the universe might offer a way to preserve the very fabric of existence, even if its form is radically altered. The Bekenstein bound, derived from black hole thermodynamics, even sets an upper limit on the amount of information that can be contained within a given region of space. This is a physical constraint that any advanced civilization would have to contend with. How much information can one consciousness hold? How much can a civilization encompass? These are not just engineering challenges. They are existential questions rooted in the very fabric of physics. So the vision of harvesting the void isn't just about a last-ditch effort for survival. It's about a profound redefinition of life, of intelligence, and of existence itself. It's about adapting to the ultimate extreme embracing the most desolate and seemingly hostile environments, and finding a spark of hope in the deepest darkness. It's about turning the universe's most fearsome devourers into its ultimate lifesavers. This isn't a future of bustling cities or vibrant ecosystems. This is a future of quiet endurance, of extreme patience, where subjective experience might be stretched to unimaginable lengths. Imagine a civilization that thinks in eons, not years. A single thought might take billions of years to complete, but from their perspective, it could feel like a fleeting moment. This manipulation of subjective time, the ability to slow down computational processes to match the dwindling energy supply, is the heart of how such beings could experience a vast amount of subjective time, even as objective time stretches into the incomprehensible future. This is the audacious proposal put forth by physicists like Freeman Dyson, who, in his 1979 paper, Time Without End, Physics and Biology in an Open Universe, laid out a scenario for how an eternal intelligence could survive indefinitely in a cooling open universe. His theory suggests that by performing computations in cycles, using a tiny fraction of their stored energy, and then hibernating for eons while the universe cools further, such a civilization could achieve an infinite number of thoughts over an infinite subjective time. It's a cosmic race against time, yes, but also a masterful dance with the very limits of thermodynamics. The idea of intelligent life, not just surviving, but thriving in its own unique way, in a universe seemingly destined for oblivion, is one of the most powerful and counterintuitive narratives in all of theoretical physics. It suggests that consciousness, this precious flame, is far more resilient and adaptable than we ever imagined. It suggests that the quest for knowledge, for experience, for simply being, might continue long after the last star is faded. From our vantage point, observing a vibrant, living universe, the thought of a cosmos defined by such desolate, vast timescales can feel overwhelming, even despairing. But for the digital descendants of consciousness, these black holes represent not an end, but a final, unimaginably long chapter in the story of intelligence. They are the last bastions of organized energy, the ultimate cosmic hearths around which the final fires of thought might flicker for a Google years and beyond. The transition from a biological existence, which draws its energy from the fleeting warmth of stars, to a digital existence powered by the faintest whispers of quantum mechanics from evaporating black holes, represents an evolutionary leap almost beyond comprehension. It's a testament to the idea that life, or rather intelligence, finds a way. It adapts, it transforms, it transcends. The universe's final, slow-burning battery becomes the last beacon of hope, not just for survival, but for a continued, albeit profoundly altered, experience of existence. This is not just science fiction. It's a profound thought experiment, grounded in the very laws of physics, that dares us to imagine a future where consciousness outlives the stars themselves. Not an end, but a final, unimaginably long chapter in the story of intelligence. They are the last bastions of organized energy, the ultimate cosmic hearths around which the final fires of thought might flicker for a Google years and beyond. The transition from a biological existence, which draws its energy from the fleeting warmth of stars, to a digital existence powered by the faintest whispers of quantum mechanics from evaporating black holes, represents an evolutionary leap almost beyond comprehension. It's a testament to the idea that life, or rather intelligence, finds a way. It adapts, it transforms, it transcends. The universe's final, slow-burning battery becomes the last beacon of hope, not just for survival, but for a continued, albeit profoundly altered, experience of existence. This is not just science fiction. It's a profound thought experiment, grounded in the very laws of physics, that dares us to imagine a future where consciousness outlives the stars themselves. We think of life as a brief candle flickering in an infinite darkness. But what if that's a failure of imagination? What if consciousness is not the candle, but the flame itself? And what if, with enough ingenuity, we could learn to keep that flame alive, even after the last star in the universe has died? This isn't just a philosophical musing. It's the audacious premise at the heart of our journey into the deepest future. A future where the very concept of time without end takes on a meaning that would shatter our current understanding of reality. For us, the passage of time is a constant, an unwavering beat of seconds, minutes, hours. Our lives are measured in heartbeats, in the cycle of days and seasons, in the span of years that feel both too long and too short. But what if time itself could become a tool, a malleable substance that intelligence could stretch and compress at will? What if the ticking clock of the universe, that grand, relentless march towards the inevitable heat-death, a state where all energy is uniformly distributed and no work can ever be done again, could be outsmarted, not by defying physics, but by embracing its deepest, most subtle principles? This is where we dive into the mind-bending brilliance of Freeman Dyson, a theoretical physicist who, in his seminal 1979 paper, Time Without End, Physics and Biology in an Open Universe, laid out a plausible pathway for intelligence to achieve an infinite subjective existence with only a finite amount of energy. It sounds like a paradox, doesn't it? An infinite lifespan from a limited power supply. It's like trying to make a single battery run a flashlight forever. Imagine for a moment that your consciousness, your very sense of you, could be decoupled from the fragile biology of your brain. Imagine that your thoughts, your memories, your entire being could be substrate independent, meaning they could exist not just in the wetware of your skull, but as information patterns, digital code, running on some incredibly advanced computational device. This isn't just science fiction anymore. The concept of consciousness being a product of information processing is a crucial underpinning for these theories. If your mind is essentially a complex program, then like any program, it can be optimized, slowed down, even paused. Now, picture this digital intelligence existing in a universe that is rapidly, relentlessly cooling. The stelliferous era, the age of stars, is long, long over. It ended roughly 100 trillion years ago, when the last red dwarf stars, those tiny dim embers, finally flickered out. The cosmos is a vast, cold, dark expanse, punctuated only by the occasional faint glow of evaporating black holes, the last beacons of concentrated energy. Even protons, the very building blocks of matter, might have decayed by this point, dissolving into radiation over timescales of 10^34 to 10^40 years. This is a universe where warmth, light, and accessible energy are rarer than gold dust. In this desolate cosmic landscape, our digital beings face an ultimate energy crisis. But they have a secret weapon: time itself. Dyson's insight was that if you perform computations in cycles, using a tiny fraction of your stored energy, and then hibernate for eons, while the universe cools further, you can stretch out your finite resources almost indefinitely. Think of it like a computer in the deepest, most extreme power-saving mode you can imagine. It wakes up, performs a single, incredibly complex computation, perhaps a profound thought, a memory accessed, a creative spark. This takes energy, but a minuscule amount. Then it goes back to sleep, powering down almost completely, becoming a silent, dormant speck of information, perhaps for 1 billion, 1 trillion, or even a googol years. It waits patiently as the cosmic temperature drops infinitesimally further, making it energetically efficient to think again, even if only for a fleeting moment. To us, this sounds like an eternity of boredom, a life of endless waiting. But this is where the aha moment truly hits you. For these beings, a trillion years of objective, external universe time might feel like a single breath, a mere blink of an eye. Why? Because their subjective experience of time is tied to their rate of thought, not the universe's objective clock. If they slow down their computational processes to match the ever-decreasing availability of energy, they can experience a vast amount of subjective time, even as objective time stretches over unimaginable eons. True immortality, then, isn't about enduring an infinite number of seconds. That's a biological, linear way of thinking. True immortality, in this cosmic endgame, is about experiencing an infinite number of thoughts, an infinite depth of experience. The goal shifts fundamentally from mere duration to the richness and depth of their inner existence. This is the beauty of the Dyson scenario. It sidesteps the seemingly insurmountable problem of finite energy by redefining what living actually means in the far future. It's a universe where consciousness becomes a patient, cosmic philosopher, contemplating the vastness of existence one thought at a time, each thought separated by an eternity of objective silence. It makes you wonder, doesn't it? If the very fabric of our subjective experience is so malleable, so open to manipulation, what does that say about the nature of our own reality, right here, right now? Are we too just running on a particular frequency, limited by the parameters of our biological hardware? And if we could choose, would we embrace an existence stretched across unimaginable eons, a single thought, taking longer than the rise and fall of empires, just to keep the flame of consciousness alive? Because while the physics might lay out a path to survival, a whisper of hope in the face of cosmic oblivion, it also ushers in a new era of questions, profound and unsettling. An era where the very definition of life, of self, and of meaning is stretched beyond anything our biological minds can truly grasp. This is where we step into a realm that feels less like science and more like myth, into the chapter we call the loneliness of gods. Imagine for a moment that you are one of these beings. You have transcended your biological form, shed the fragile vessel of flesh and bone that once confined you to a mere blink in cosmic time. You are now pure information, a cascade of data, a pattern of consciousness woven into a substrate of unimaginable durability, perhaps a computational matrix designed to endure the eons. This isn't just a fancy thought experiment. The concept of substrate independence is a cornerstone of these theories, positing that consciousness is about the pattern of information, not the specific biological hardware it runs on. If your mind is simply complex information processing, then theoretically, it could be uploaded, copied, or transferred to any suitable medium. But here's where the existential knots begin to tighten. If your consciousness, your very self, is uploaded, transferred from a biological brain to a digital one, is that still you? This isn't just a parlor trick. It's the ancient philosophical dilemma known as the ship of Theseus paradox, writ large across the cosmos. The old Greek thought experiment asks, if a ship has all its planks replaced one by one, is it still the same ship? And if you replace every single neuron, every memory, every synapse of your brain with a digital equivalent, is the resulting digital entity you, or merely a perfect, indistinguishable copy? Think about it. The original biological you, might still exist, still breathing, still feeling, still wondering. But now there's a new you, an exact replica, living in a commutational cloud. Which one holds the authentic spark of your being? What if the biological you then dies? Does the digital you inherit your legacy, your identity, your very soul? Or is it simply a ghost in the machine, a perfect simulation, haunted by the memory of a life it never truly lived in the flesh? This isn't just a philosophical debate for a dusty university hall. For beings contemplating a digital exodus, it's the most fundamental question of their existence. It's the ghost in the machine narrative, but the ghost is you, and the machine is your new immortal body. And what about the ethics of such an existence? If consciousness can be copied, can it be multiplied? Could a single original consciousness spawn countless digital echos, each believing itself to be the authentic you? What are the rights of these digital entities? Do they possess the same moral standing as biological beings? If they can experience joy, suffering, memory, love, what responsibilities do we, as their potential creators or predecessors, bear towards them? These aren't easy questions, and they lay bare the profound moral landscape that would precede and define a truly post-biological civilization. Now, let's fast forward, way past those initial dilemmas. Let's assume that humanity, or whatever intelligent life has inherited the universe, has navigated these treacherous waters. They've embraced substrate independence, overcome the ship of Theseus paradox by perhaps accepting a new, more fluid definition of self, and have found a way to digitize their consciousness, achieving a form of immortality. They've mastered the art of slowing down their internal processes, just as Freeman Dyson theorized in his seminal 1979 paper, Time Without End, Physics and Biology in an Open Universe. They're now thinking in cycles that might take eons of objective time to complete, allowing them to experience an infinite subjective duration within a finite energy budget, even as the universe inexorably cools and expands. They've seen the stelliferous era, the age of stars, draw to a close, a cosmic twilight that ended approximately 100 trillion years after the Big Bang, when the last red dwarfs flickered out. They've witnessed the slow, agonizing decay of matter itself, as protons, if they are indeed unstable, broke down into radiation over timescales of 10^34 to 1040 years. They've huddled around the last cosmic campfires, evaporating black holes, harnessing the incredibly faint trickle of Hawking radiation. Imagine a civilization, not just surviving, but thriving in its own subjective way. For 200 years, the time it takes for a supermassive black hole, the size of a galaxy, to completely evaporate. This isn't just about outliving the universe. It's about becoming its ultimate custodians, its last witnesses. And what a universe they would be witnessing. Not the vibrant, star-studded tapestry we know, but a vast, cold, dark emptiness punctuated only by the occasional, almost imperceptible burst of energy from a dying black hole. The Second Law of Thermodynamics, first articulated by Lord Kelvin in the 1850s, has done its work. Entropy has reached its maximum. All energy is uniformly distributed, and no work can be done. This is the heat death, not a fiery inferno, but a state of ultimate frozen equilibrium, where the very concept of event loses its meaning. These beings, these gods of the end times, would be the sole inheritors of this desolate landscape. Their existence would be a continuous internal monologue, a subjective eternity of thought and memory. They would possess the accumulated knowledge of everything that ever was, every star that ever shone, every civilization that ever rose and fell. They would be the ultimate archives, the living library of a dead universe. This is the heart of our metaphor. The last intelligent beings are like the sole librarians of a library, containing the memory of the entire universe, but with no one else to read the books. Think of the sheer weight of that memory. Every joy, every sorrow, every triumph, every tragedy, from the dawn of time to the heat death of the universe, all held within their collective consciousness. Ludwig Boltzmann, in the 1870s, gave us the statistical definition of entropy, linking it to the number of possible microscopic arrangements of atoms. These beings would hold the entire statistical history of all arrangements, all information. But what is the value of a memory if there's no future to apply it to, no new experiences to enrich it? What is the purpose of knowledge when there's no one left to share it with, no new questions to answer, no new discoveries to make? This brings us to the profound aha moment of this chapter. The physics might make survival possible, but the ultimate question is whether such an existence is desirable. Is an infinite life of memory and solitude a victory, or the most profound curse imaginable? Imagine the sheer loneliness. You are eternal. You are powerful in a way, able to manipulate information and energy on cosmic scales, albeit incredibly slowly. But you are utterly, profoundly alone. The accelerating expansion of the universe, discovered in 1998 and attributed to dark energy, means that even other distant civilizations, if they exist, would eventually become causally disconnected, forever beyond reach. There would be no other lights in the cosmic dark, no other voices to answer your own. Just the vast, empty, silent canvas of a universe that has played out its final act. What would give meaning to such an existence? Our human lives, brief as they are, derive much of their meaning from their finitude. The preciousness of time, the urgency of love, the drive to create, to leave a legacy. These are all sharpened by the knowledge that our candle will eventually flicker out. But for these eternal beings, there is no end. There is no urgency. There is no legacy, because there is no one left to receive it. Just an endless now, stretching into an unimaginable abyss of objective time. Would they eventually succumb to a kind of cosmic ennui, a profound weariness born of infinite repetition and ultimate solitude? Would the sheer burden of infinite memory become a torment rather than a treasure? Every single event, every mistake, every loss, preserved with perfect clarity for all eternity. We humans often cope with trauma by forgetting, by moving on. But what if moving on is no longer an option? What if every single moment of cosmic history is forever accessible, forever re-experienced? Even the act of thinking, of computing, would be stretched to the breaking point of comprehension. As Dyson envisioned, they would periodically shut down, hibernating for eons to conserve energy, only to awaken and perform a few more calculations before plunging back into subjective slumber. A single thought could take longer than the lifespan of a star. Imagine trying to hold a coherent thought for 1,000,000 years or 1,000,000,000. The very nature of what it means to think would be utterly alien to us. The Bekenstein bound, which sets an upper limit on the amount of information that can be contained within a given region of space, and Landauer's principle, which states that erasing one bit of information dissipates a minimum amount of energy, highlight the fundamental constraints on even this digital existence. Every thought, every memory, every computation would come at an energy cost, however minuscule, in a universe rapidly running out of anything to spend. Some might argue that the very act of preserving consciousness, of extending life beyond its natural limits, is an inherent good. Frank Tipler, in his 1994 book, The Physics of Immortality, proposed his omega point theory, suggesting that intelligent life must eventually engulf the entire universe and process an infinite amount of information before a final cosmic singularity. In his view, this ultimate act of information processing could resurrect every being that ever lived, creating a form of universal immortality. But even in Tipler's grand vision, the question of meaning and purpose in such a final, all-encompassing consciousness remains. Perhaps the purpose of these gods of the end times would simply be to remember, to be the conscious archive of all that was, a living monument to a universe that has otherwise faded into nothingness. They would be the ultimate narrators, the keepers of all stories, but with no audience to hear them, save for themselves. They would be the memory, but also the forgotten. A silent, eternal vigil in the cosmic dark. This isn't just about the survival of intelligent beings. It's about the survival of meaning. When you strip away all external stimuli, all novelty, all interaction, all possibility of growth or change, what is left? Is it truly a victory to exist in such a state, to be the last flickering flame of consciousness in a universe that has long since died around you? The physics, as we've explored, offers tantalizing pathways for intelligence to outmaneuver the seemingly final decree of the universe's heat death. It points to the incredible resilience of information, the malleability of time, and the ingenuity of life to adapt, even to the most extreme cosmic conditions. But the ultimate question, the one that lingers long after the equations are solved and the simulations run, isn't about how we might survive. It's about why. And whether, in the end, such a survival is a gift or a curse. This contemplation, this profound philosophical challenge, is what awaits any intelligence that dares to reach for true cosmic immortality. It's a journey not just through space and time, but through the very essence of what it means to be, to feel, to remember. And it leaves us with an unsettling thought. If we could truly become gods, eternal and all-knowing, in our final desolate dominion, would we find paradise, or simply the most profound loneliness imaginable? And it leaves us with an unsettling thought. If we could truly become gods, eternal and all-knowing, in our final desolate dominion, would we find paradise, or simply the most profound loneliness imaginable? Perhaps then, the ultimate act of defiance against cosmic oblivion isn't merely to endure, to shrink our consciousness and cling to the last whispers of energy in a dying cosmos. Perhaps it's something far grander, far more audacious. We've spoken of consciousness as a flame, a fragile flicker against an infinite darkness. But what if that flame, once nurtured and grown, isn't meant to merely survive the night? What if its true destiny, its highest purpose, is to light a new candle? This is where the story of immortality takes its most mind-bending turn, pushing beyond the boundaries of this universe and into realms that sound like pure science fiction, yet are whispered about in the hallowed halls of theoretical physics. The idea isn't just to outlive the universe, but to outcreate it, to become the architect of a new beginning, ensuring that when our candle finally sputters out, another, vibrant and full of potential, has already been lit. Imagine a civilization having mastered the art of subjective eternity, having harnessed the last vestiges of energy from evaporating black holes, existing as pure information, thinking in aeons rather than seconds. They've navigated the treacherous philosophical waters of identity, of what it means to be you, when your essence is a digital pattern, substrate independent, capable of existing on any suitable medium. They have become the ultimate librarians of a dying cosmos, preserving every memory, every triumph, every whispered secret of a universe that is fading into a cold, dark silence. They've seen the stelliferous era, the age of star formation, come to an end, roughly 100 trillion years after the Big Bang, witnessing the last red dwarf stars flicker out like dying embers. They've watched as baryonic matter itself, the very stuff of you and me, began to dissolve into radiation, a process that, if proton decay occurs, could effectively conclude around 10 to the 40 years. They've huddled, metaphorically speaking, around supermassive black holes, harvesting the incredibly faint but persistent Hawking radiation that promises a final dwindling energy source for an unimaginable 2x10 to the 100 years. They've learned to slow their internal processes, to stretch their subjective experience of time, to make every joule of energy count, existing in cycles, hibernating for eons, just as Freeman Dyson theorized in his seminal 1979 paper, Time Without End, Physics and Biology in an Open Universe. But even for such an intelligence, such a resilient, patient, and infinitely wise collective consciousness, the heat death of this universe remains an inescapable thermodynamic decree. The second law of thermodynamics, first extrapolated to the cosmos by Lord Kelvin in the 1850s, is a relentless master. It dictates that entropy, the universe's total disorder, will always increase, inevitably leading to a state of maximum equilibrium, where no work can be done, no information processed, no thought conceived. Ludwig Boltzmann, in the 1970s, gave us the statistical mechanics to understand this, linking entropy to the sheer number of possible microscopic arrangements of atoms. The universe, in its ultimate end, will be a vast, cold, empty expanse, devoid of any meaningful activity. For an intelligence that has come so far, that has conquered biological limitations and defied cosmic timescales, to simply accept this finality feels incomplete. It feels like a surrender. And perhaps, for the ultimate form of intelligence, surrender is not an option. This is where the concept of the next flame truly ignites. The idea that the most profound act of immortality isn't merely to survive the end of this universe, but to create a new one. To use the accumulated knowledge, the harnessed energies, and the sheer computational power of an entire cosmos-spanning civilization to become a genesis point for a fresh reality. Think about it. We've come to understand that our own universe likely began from an incredibly hot, dense state, expanding rapidly in an event we call the Big Bang. And many cosmological theories, especially those stemming from inflationary cosmology, suggest that our universe might not be the only one. What if, within the vast quantum foam of reality, there are endless possibilities for new universes to spontaneously nucleate, to bubble off from a larger pre-existing space-time? If such phenomena are possible naturally, then what if an intelligence, having evolved for trillions upon trillions of years, could learn to instigate such an event, to become quite literally a cosmic midwife? This isn't about some fantastical, magical creation. This is about understanding the fundamental laws of physics so deeply, manipulating the fabric of space-time and energy at such a minuscule, precise level that you could trigger the birth of a new reality. Imagine a civilization that has mastered quantum gravity, that can manipulate singularities, that understands the very information content of space-time itself. The Bekenstein bound, for instance, sets an upper limit on the amount of information that can be contained within a given region of space, a concept born from black hole thermodynamics. An advanced intelligence might understand how to push against or manipulate such fundamental limits to initiate a new cosmos. Their final collective project isn't about sustaining themselves forever in the darkness. It's about building a cosmic incubator, leveraging insights from John von Neumann's work on self-replicating machines from the 1940s They might design and deploy incredibly complex, self-assembling automata, not just to survive, but to create. These machines wouldn't be for building habitats or harvesting stars, but for manipulating the quantum vacuum, for sculpting the primordial conditions necessary for a new Big Bang. The process would be slow, painstaking, unfolding over subjective eons. It would involve the ultimate application of the information paradox, a challenge first posed by Stephen Hawking in 1974. If information truly cannot be destroyed, as quantum mechanics suggests, then perhaps the seed of a new universe could be infused with the accumulated wisdom, the very essence of the dying one. The hope would be to preserve not just life, but potential itself. They would be performing the most profound act of genetic engineering imaginable, not on a single organism, but on reality itself. They would be crafting the initial conditions, the fundamental constants, the very laws that would govern this newborn universe, not to create a perfect, sterile utopia, but to ensure that it has the potential for complexity, for evolution, for life, and ultimately for new consciousness to emerge. This isn't just about saving themselves. It's about saving the idea of consciousness, the potential for wonder, curiosity, and meaning. It's the ultimate legacy. And what if creating a new universe is simply too hard, too risky, or even impossible? What if, instead, the ultimate act of immortality is to find a way to traverse the multiverse? The idea of a multiverse is not new, nor is it confined to comic books. Many theoretical frameworks in physics suggest it. Inflationary cosmology, for example, posits that the rapid expansion of the early universe might have created an infinite number of bubble universes, each with potentially different physical laws and constants. String theory, with its higher dimensions, suggests our universe could be just one brain, floating in a much larger multi-dimensional bulk, with other brains representing other universes. The many worlds interpretation of quantum mechanics even suggests that every quantum measurement causes the universe to split into multiple parallel realities. For an intelligence that has reached the gods of the end times level of capability, the ability to jump between these cosmic bubbles, to find a fresh, vibrant universe to call home, might be a more achievable form of ultimate immortality. Imagine the technology, not just manipulating gravity or space-time within our universe, but manipulating the very boundaries between universes, opening wormholes not just to distant stars, but to entirely different realities. This would be the ultimate migration, not from one planet to another, or one galaxy to another, but from one cosmos to another. A cosmic exodus carrying the flame of consciousness across the void between realities, seeking a new candle to light. Such a journey would be fraught with unimaginable peril. What if the fundamental constants of another universe are incompatible with the very structure of their digital existence? What if the laws of physics are so different that their essence, their information, would simply unravel? These are the ultimate unknowns, the cosmic gambles that a truly immortal intelligence would have to face. But the reward would be not just continued existence, but renewed potential, to experience a new Big Bang, to watch new stars ignite, new galaxies form, new life evolve, all through the lens of an ancient, infinitely wise consciousness. It would be the ultimate scientific endeavor, the ultimate philosophical exploration. The aha moment here is profound. The ultimate form of immortality may not be endurance, but creation. The final purpose of intelligence might be to ensure that when our universe ends, another one begins, seeded with the potential for new life and new consciousness. It transforms the narrative from a race against cosmic oblivion into a cosmic act of propagation. It's the ultimate legacy, the passing of the torch, or rather, the lighting of a new flame.